Filter banks consist of a bank of subband filters which cover the entire frequency band of our signal, followed by downsampling in the analysis filter bank and preceded by upsampling in the synthesis filter bank. This can be seen in the following pictures. So here we have the analysis part, here we have the downsampling, and here we have the synthesis part, and here we have the upsampling. In the picture, x of n is the input signal, for instance, our audio signal. Y subscript k of n are the downsampled subband signals, with k the subband index and m the index at the lower sampling rate, and x hat of n is the reconstructed signal. So we have here the reconstructed signal. As described in lecture 2, the down arrow capital N symbolizes downsampling by a factor of n, including removal of zeros. If x of n is the signal we downsample, then we also write the downsampled signal this way. So we see we have m times capital N plus n0, where n0 is the index of the first sample we keep in the downsampling, or the phase, with n0 greater or equal to 0, n smaller and equal to n minus 1. The up arrow n symbolizes upsampling by a factor of n, including insertion of zeros. If y of m is the signal we upsample, then we also write the upsample signal as, so we have here y of superscript n0, subscript n0, superscript up arrow capital N of n. It's equal to y of m when n is equal to m plus capital N plus n0, or 0 elsewhere, where n0 is the index of the first non-zero sample in the upsampled signal, or the phase. So the only hope we have to obtain perfect reconstruction with non-ideal filters and still critical sampling in filter banks is that somehow the aliasing from different subbands cancels out during the synthesis process when we add up all the subbands. If we add, for example, the low pass signal and the high pass signal for the reconstruction, or in other words, we would like the sum of all aliasing components at the output of the synthesis filters to become 0. The question now is, how do we obtain this goal?